projector. It sounds lit over there. Smaller head. Nice. Smaller head. It's fine, look, there's the meat echo, yeah, I can see over there. Yeah.
Okay then.
Hello.
So, in my mic is that where you want to play your garbage cans on presentation?
Good afternoon. That was super deliberate. Now that you're all awake, let's get started. It's not just my mic, Brian. All right. I'm not repeating Brian's comments to the mic, but let's get started. This is ICCRG. If you don't care much about congestion control, you're in exactly the right room. You might learn a few things. This is an IETF meeting, but we are going to still use the note well. I'm not going to read this, and if you haven't read it, you probably should. Moving along, before I get into the agenda, I believe we have a Jabber scribe. Do we have? No, sorry. We have somebody to cover Jabber. Do we have a note taker? You're covering Jabber, right? Yes. Oh yeah, sorry, you there. Thank you, Tom. I know Tom. It's late in the afternoon and late in the week. I need somebody to cover Jabber then. Oh, hang on. I need somebody to take notes. Yes. I'll get this right eventually. Don't worry. There's such a thing called eventual consistency. Sorry? Yes, that would also work for me. But it's ideal if there's one person at least who commits to doing this.
I'll do it.
Thank you, sir. I heard a voice. I didn't see. Yes, Brian. Thank you. Thank you. Moving on. We have a packed agenda today. We have only 4 presentations, but all 4 of them interesting talks, and so there's a fair bit of time for each one. I'm going to try and stick to the time that I have written out there, and as always, you will all go past the time. So we'll see how this goes. I don't have very much else here to talk about for the agenda. Anybody want to bash the agenda? And done. All right, Neil, you're up.
Let's see, how's this mic? That's pretty good. All right. So I'm going to be talking about BBR v2, which we think of as a model-based congestion control. This is joint work with my colleagues at Google, Yu Chang, Sohail, Ian, Victor, Priyaranjan, Yusuk, Matt, and Van Jacobson. Next slide, please. So I'm going to focus on the BBR v2 research update, talking about improvements between BBR v1 and v2. Talking briefly about the status and recent results we're seeing in experiments, and then try a sort of lightning review of the BBR-v2 design, some of which we talked about previously at previous IETFs, and then give a quick status summary and conclusion. Next slide, please. Oh, yes. Perfect. All right. So in order to address some various issues with the initial BBR v1 version, we have undertaken a couple improvements. So the main issues we're addressing here with v1 included low throughput for Reno and cubic flows, sharing bottlenecks with bulk BBR flows in certain scenarios. BBR v1 was loss agnostic, which in certain scenarios with bottleneck buffers or AQMs, keeping the queue at 1.5 BDP or shorter, that could result in high packet loss rates. V1 was ECN agnostic as well, did not use ECN signals. And with the initial release, there could be low throughput for paths with high degree of data or ACK aggregation. And here, the biggest issues we would see with Wi-Fi paths with low RTTs, say 1 to 10 milliseconds. And then another issue with V1 was that there could be pretty severe throughput variation due to quite low C1s in the small period of time that they were in probe RTT mode. And with BBR-V2, we were trying to tackle all of these issues. And I'll give some examples of the design changes and the resulting behavior now. So for coexistence with Reno and Cubic, the basic approach we take with BBR-V2 is to try to adapt the timescale of the bandwidth probing so that we can coexist better with Reno and Cubic. And we talked about the details of the algorithm last July at IETF102, and those are basically the same in the latest revision as well. And here's a quick diagram to sort of illustrate the flavor of behavior that we're talking about here. So here's a scenario with a 50 megabit bottleneck link, a 40 millisecond round trip time, 1 BDP of buffer, 4 cubic flows, 1 BBR-V2 flow. And you can see the BBR-V2 flow is playing along nicely there at the bottom in the pink, achieving an approximately fair share with a reasonably low retransmit rate matching cubics here. So the next major improvement is using packet loss as an explicit signal with an approach that sort of has an explicit target loss rate ceiling, which I'll talk a bit about later on. This we also talked about at IETF 102. And here's a quick scenario just to sort of illustrate the behavior with this algorithm. So here we have 6 BBR-V2 flows in a very shallow buffer that's only 5% of the BDP, only 41 packets. But the flows start staggered and achieve an approximately fair share and with a reasonably low retransmit rate given how shallow the buffer is. So BBR-V2 uses ECN as a signal now, DC TCP style ECN if it's available to help keep the queues short. And to illustrate the kind of behavior we're talking about here, we have 20 BBR-V2 flows starting staggered every 100 milliseconds. It's a 1 gigabit bottleneck link and a 1 millisecond round trip time. The ECN marks here are from the Linux CODL QDISC with the default settings except for the CE marking threshold at 242 microseconds, which is about 20 packets worth of queue. And here we have 0 retransmits, pretty decent fairness, and RTTs are fairly low. The median RTT is right around the marking threshold, and the rest are reasonably well controlled. So there are also improvements for high throughput for paths with large degrees of aggregation, notably, as I said, Wi-Fi. And to achieve that, V2 explicitly estimates the degree of aggregation that it's seen recently. And that may be in the data path, it may be in the ACK path. Either way, the aggregation shows up in the ACK stream, and BBR tries to characterize that. And we talked about the details of that at IETF 101 last March, so you can find the slides there. On YouTube, we're seeing BBR-V2 match cubic throughput for users specifically on Wi-Fi links and overall. And in control tests, we're seeing reasonable behavior. You can see here on the right is a time sequence plot of a BBR-V2 transfer to my laptop at home. So it started at a POP in New York City, went over the local internet through a DOCSIS link, which has its own aggregation behavior, through a Wi-Fi link, has its own aggregation behavior, and still behaves reasonably well. And the aggregation modeling code is available in Quick, in the Chromium Quick, and now recently also in Linux 5.1. The final major design change is to reduce the throughput variation. So in BBR-V1, if you had to enter probe RTT, perhaps because it was a bulk flow that's been going more than 10 seconds or so, BBR-V1 would cut the C1 to 4 packets. In V2, we can cut the C1 to 50% of the BDP to still achieve reasonable throughput, even while attempting to probe the two-way propagation delay. So those are the major improvements in V2. As a quick summary, you can sort of consider how V2 lines up with V1 and cubic. As I said, it's a model-based congestion control, and here specifically the model parameters that we feed into the state machine for BBRV2 include the throughput, the RTT or min RTT, the max degree of aggregation we've seen recently, and the max amount of data we think it's reasonable to keep in flight. And as I said, BBRV2 has a sort of explicit loss rate target and an explicit response to congestion, to DC-TCP style congestion. And the startup, not surprisingly, has a sort of slow start style behavior, doubling the throughput until we see either the throughput plateau or the ECN or loss rate exceed the design parameter threshold. So where are we with BBRV2? Right now we're testing it with YouTube TCP traffic. We have a kernel with an initial version of BBRV2 on all the YouTube machines, and it's running a global experiment with a small percentage of YouTube users. Results so far are looking quite reasonable. We see the RTTs are, of course, vastly lower than cubic and even a little bit lower than BBRV1. The packet loss rates are considerably reduced versus BBRV1. They're about halfway down back to cubic, and while still matching cubic throughput. And we're continuing to iterate using the YouTube setup, other production tests and lab tests. And we're preparing to open source the code as soon as we can. And as we do that, as soon afterwards as possible, we're going to update the BBR internet drafts to reflect the latest BBRV2 code, because I know there are people out there that are interested in working with the algorithm based on the draft rather than the code. I would note that the code we have made a dual BSD GPL, so hopefully folks in the BSD ecosystem can use it as is if they are interested. But anyway, so I'm going to try to do a lightning overview of the BBRV2 design. How much more time do I have, China? I guess
20 minutes, but you should probably leave room for Q&A.
Yeah. Okay.
Will you take a clarifying question, Neil?
Yeah, sure.
So this is the JavaScribe. Ingmar Johansson asks, which RTT is it on slide 6?
That's the min RTT, our estimated two-way propagation delay. So just a quick, I'm going to try to do a lightning overview of the BBRV2 design. Many of these slides we've shown at previous IETFs. I just thought it would be useful to have a quick overview all in one spot. At a 10,000 foot view, you can think of the design as basically consisting of a system that takes as inputs measurements from the network traffic that it's controlling, and it's looking at a couple different signals, the throughput or delivery rate, the delay, that is the RTT delay, the loss events, ECN mark events, and those are all fed into a network path model inside BBR. And then the parameters of the network path model are used to control the evolution of the state inside the state machine, inside BBR. And then that in turn makes adjustments in the output parameters, which are the rate, which you can think of as a sort of pacing rate for the sending process, the maximum volume of in-flight data, otherwise known as a congestion window or CWIND, and then what I'm calling here a quantum, which is just sort of a chunk size for the whatever offload mechanism might be in play, whether it's TSO or GSO or whatever the OS calls it. And those output parameters are fed into the sending engine of the transport, whether it's TCP or QUIC or something else, which takes the data, chops up into quantum size pieces, and then paces them out at the given rate until it has a maximum amount of data or until pacing says you can't send any more right now. So that's the big picture. If we look at drill down into the model and what's inside the model, you can sort of visualize it as is depicted here in the diagram. That's a time sequence diagram with the sequence on the y-axis, time on the x-axis. The green is showing send events. The acts are showing up as blue here. Here I've drawn them as pretty bursty acts because these days that's a pretty typical behavior, whether it's high-speed Ethernet Wi-Fi, cellular, DOCSIS, they all have aggregation at pretty significant levels. And you can sort of visualize each of the parameters here. The first one is the maximum bandwidth that's available recently to this flow. The second one you can think of as the min RTT seen recently, which serves as an estimate of the two-way propagation delay. Then there's the maximum amount of in-flight data that we think is reasonable based on recent loss and ECN signals. And then there's the maximum measured aggregation level that we've seen recently in the ACK stream. And two of these in particular, of course, are going to change quite rapidly based on the low traffic levels. That is the bandwidth and the maximum in-flight that's reasonable to keep, maximum amount of data that's reasonable to keep in flight. So because of that, BBR-V2 maintains both a short-term bandwidth and in-flight estimate and a long-term bandwidth and in-flight estimate. And you can think of this as sort of being analogous to QBIC, which has a sort of short-term SS thresh estimate, and then a longer-term WMAX value that's a higher amount of in-flight data that it's hoping to quickly progress back up to if everything goes well. It's sort of analogous to that. So at a high level, the adaptation of the model basically estimates that bandwidth and in-flight 2D set of parameters over both the short term and the long term, with the goals being, not surprisingly, high throughput. And for BBR, importantly, we're trying to be able to maintain that even when experiencing some moderate particular amount of random packet loss. And then we're, of course, trying to keep low queue pressure. And the basic approach here is sort of twofold. We want to spend most of the flow's time in a phase where it's mostly adapting quickly to try to maintain flow balance between the ACK stream and the data stream, while also leaving some headroom of unutilized capacity, either in the bottleneck queue or in the bottleneck link. And to do that, we have this short-term bandwidth and in-flight estimate tuple that basically bounds the behavior using the latest delivery process and loss and ECN signals that we're seeing. And the intuition here is basically, what's the bandwidth and in-flight delivery process that we're seeing right now? And if we're seeing ECN or loss signals, that's an indication that we need to adapt quickly to those signals that we're seeing right now to maintain reasonable queuing levels. And then the second part of this picture is that, of course, periodically we do need to probe beyond that flow balance level to probe robustly to see if higher bandwidth is available now than, say, it was available before the last time we probed for bandwidth. And to do that, to control that behavior, we have the, as I said, the longer term bandwidth and in-flight estimates that were have been most recently measured before we saw signals of congestion in the form of ECN or loss marks. And the intuition with that part of the picture is that we're basically trying to say, what's the maximum bandwidth and in-flight that can be achieved consistent with the network's desired loss rate and ECN mark rate, SLOs, or service level objectives. So that's the basic high-level picture of the model. So before we consider the details of how it evolves, I think it's useful to consider a more concrete example. So it's an interesting question. How do we adapt to a packet loss signal given the ambiguities involved? So if we consider this example, here we have a shallow buffered high-speed WAN with, say, 100 millisecond round trip time. An app does occasional 2,000 packet writes. Maybe those are RPC requests, RPC replies, web object replies, something like that. And let's consider a case where the available bandwidth drops from something really high, say 12 gigabits per second, down to 12 megabits per second, which is from 1,000 packets per millisecond down to 1 packet per millisecond. And of course, that's a big drop. So in the first write after that bandwidth drops, if we're continuing at the same rate, there will likely be very high packet loss. And there's an interesting ambiguity, though, about the low delivery rate that we see there of 2 packets in the round trip time. There's a question of to what extent is that due to the lack of data that was sent, to what extent it was due to bursty traffic that may have caused that loss, or it could be a sustained reduction in the bandwidth available to that flow. So the question is, what do we do there? So the philosophy here, the design philosophy here is that to fully utilize bottlenecks of all kinds, including bottlenecks with shallow buffers, we want to adapt both the maximum sending rate and the maximum in-flight we allow. So in this example, should we have simply cut the C-wind right down to 2 due to only 2 packets being delivered? Well, it's interesting to consider that if we actually find a way to pace at the available bandwidth, we can actually deliver far more than 2 packets per round trip time. So the idea here is that if this loss pattern or something like it continues repeatedly, we basically want to gradually reduce the sending rate down to match the available bandwidth and to try to converge to an in-flight that matches the new BDP so that we can send the entire response without anything being dropped. That's the basic motivating idea. So what does the algorithm look like for the short-term model adaptation? Basically, this strategy at a high level is to gradually adapt, as I said, to the measured delivery process, which includes both the bandwidth and the volume of data. And this adaptation applies generally whether we're in fast recovery, RTO recovery, not in recovery at all, whether we're application limited or not. And the basic idea is to maintain a very recent estimate of the delivery process, both the rate and the volume of data. And then upon, once per round trip time, make an adjustment in those 2 model parameters. That is a multiplicative cut by 30%, somewhat like cubic, except the twist here is that we try not to cut the model parameters below the most recently observed delivery process values, so that we try not to overreact and try to match the recent or converge down to the recent delivery process. So that's the basic idea. So so that's the model and how that evolves. If we switch over to the state machine, at a high level, the state machine is quite similar to V1. We're alternating essentially between probing for bandwidth and round trip time. When the connection's warming up, we have a startup phase. It's a lot like slow start. Once the path we think is full, we try to drain the queue. And then we alternate between probing for bandwidth and probing for round trip time. So just to quickly go through an example life cycle of a BBR-V2 flow. Here I'll try to highlight in bold the stuff that's new in V2 versus V1. And a lot of this may seem similar if you recall the presentation from last July, but I thought it would be useful just to run through it quickly again. So a flow starts out in startup, which like the traditional slow start phase, we're trying to rapidly discover the available bandwidth by doubling the sending rate every round trip time until we see that it looks like the path is full, either because bandwidth samples are plateauing or the loss or ECN mark rate becomes too high. When we think we've filled the pipe, then we try to drain it, draining that queue, and also if we've seen ECN or loss marks that indicate that we've bumped up against some queue level, then we try to leave some headroom as well. Then we try to spend most of our time in a phase that you can think of as sort of a cruising, where we're trying to maintain a low in-flight and adapting continuously every round trip time to whatever loss in ECN signals that we see based on the algorithm I just described. And then when we decide it's time to probe for bandwidth, first we try to refill the pipe by sending out exactly the estimated bandwidth. So hopefully we're refilling the pipe without creating any queue for doing well. And then we proceed into a phase where we're raising in-flight to a level that may indeed be likely to be creating some kind of queue. And we don't know whether that's a shallow buffer that we're dealing with or a deep one. So we start out cautiously with a 1 extra packet in flight and then progress to exponentially higher amounts as we were able to grow in flight without causing the ECN mark rate or the loss rate to go above the design SLO thresholds. And then once we do see some indication that we filled the path, either because we were able to, we apparently created a queue by having in-flight reach some multiple of the BDP, or we hit ECN or loss signals, then we try to drain the queue that we've created and leave some unused headroom again if we saw a loss or ECN. So that's the basic life cycle of a BBR flow. And to summarize, I can sort of run through a quick comparison of Reno and Cubic and BBR v2. So Reno has this sort of familiar sawtooth pattern with putting an additional packet in flight every round trip time until it experiences any packet loss at all. And that response to any level of packet loss at all means it has sort of a brittle loss response. And because the C1 increases are linear, 1 packet per round trip time, it needs a long time to fill a pipe. So it needs 1,000 times more time to reach 1,000 times higher bandwidth, which means, for example, to fill a 10 gigabit, 100 millisecond path, you need more than an hour between any sort of packet loss at all, which means you need a very, very low packet loss rate of 2 times 10 to the minus 10, which is not really achievable in practice. So people came up with Cubic, which has a more scalable growth curve using a cubic increase function, but it's still not as scalable as we'd like. So you still need, since it's a cubic function, you still need 10 times more time if you want to reach 1,000 times higher bandwidth. And so, for example, if you have a 10 gigabit link with a 100 millisecond round trip time, you need more than 40 seconds without any packet loss whatsoever. So still you need a fairly low loss rate of sort of 1 packet in 30 million. So with BBR-v2, what we're trying to achieve is a more loss tolerant design with a more scalable growth function, and also to leave more headroom in the steady state than Cubic does. So the idea here is that we try to have a scalable exponential growth so that you can utilize nearly available bandwidth in logarithmic time. And you, because of the loss tolerance, you can fully utilize even big BDPs that even with a certain amount of loss in every round determined by the design parameter. That's the loss thresh. And this is a picture of a shallow buffer case where we do run into packet loss. If there is a deeper buffer, then we wouldn't even be running into that packet loss. A quick status overview. BBR-v1 is running for most traffic on Google.com and YouTube and inside the Google backbone, but we are experimenting with BBR-v2 on YouTube. There are some links there to other documents that we've talked about before. And in conclusion, we're actively focused on BBR-v2 and making improvements there, including reducing queue pressure, improving coexistence with Reno and Cubic. There's also work going on BBR for FreeBSD TCP at Netflix, so we're in close communication with their excellent team. And as always, we're happy to see patches, hear test results, look at packet traces. We encourage people to offer ideas about the algorithm, edits for the internet drafts, typos, bug fixes, whatever you have. We're happy to hear it. Thank you very much.
Thank you, Neil. We have about 7 minutes for questions.
Hello. JavaScribe. Dave Tat asks, oh no, I've lost it. Have you tried the existing RFC 3168 compliant FQ CODL response?
We have not experimented with that in the Google in the BBR Google version of BBR TCP or Quick. No, we're bigger believers in a direction where ECN is more like in DC TCP or L4S, where there's an ECN response whenever that happens at lower queue levels and where the sender has a more graduated proportional response to the ECN. We believe in that direction is a good direction to go.
Okay, I have 2 more from Jabber and then I'll drop back. Mario Hawk asks, which mechanism achieves a convergence to fairness among multiple BBR2 v2 flows?
Yeah, so it's going to depend on whether we're running into a buffer limit or not. So if it's running into an ECN or loss buffer limit and setting implied high, the fairness is achieved by the multiplicative decrease, which leaves that headroom, and the amount of headroom that's left is proportional to the in-flight high of the flow. So bigger flows are leaving more headroom. It's very similar to the convergence dynamics of Reno or cubic because of that multiplicative decrease effect. If there's no buffer limit that's being run into, then the convergence happens because of the dynamics of the way the bandwidth probing works. And it's a little more subtle, and we can cover it offline for anyone who's interested in the details, but basically smaller flows, when they probe for bandwidth, their multiplicative increase makes a larger proportional increase in their delivered bandwidth than the proportional increase that a higher bandwidth flow sees when it probes. I can run through the details offline or over email if people are curious.
Okay, and then John Border asks, is there something that can be done in a browser to always get a BBR response from YouTube?
No, although from YouTube, you're always going to get a BBR of some flavor, either mostly V1, sometimes V2, if you're randomly selected.
Hiren from Cloudflare. So drain phase has changed now. We are not draining all the way, as in we are not bringing sending rate down to 4 packets, but we are at much higher rate now. So I thought the idea was to get min RTT out of it.
Right. So that's the probe RTT phase there. Yeah. Instead of going down to 4 packets, going down to half the BDP. The intuition there is that at a high level, to first approximation, if you can keep exactly the BDP in flight, then that will give you an MTQ. So if you happen to know exactly the bandwidth and exactly the RTT, then if you pull it down to 1 BDP, you'll get an MTQ. Since you don't always know exactly your available bandwidth and the real underlying two-way propagation delay, we cut it down to half to give ourselves the ability to gradually converge down to everybody seeing the two-way propagation delay. But the basic answer to your question is that once the amount of data in flight is less than the BDP at any level, then in theory you have the ability to see the two-way propagation delay.
Okay, and I guess between 4 and 50%, like the rationale to get 50% is because we are almost doubling. Is that in the startup phase? Like what's the
No, it's not
rationale?
really related to it's more a question of how far do we need to pull down the in-flight to be able to converge, given that when the flows start out, there might be quite a bit of queue and people might not really have a good estimate of the two-way propagation delay. So when they try to estimate the BDP, that estimate is not going to be perfect either. So cutting to half of something that's more than 2 times bigger than what it ought to be is not going to give you a good answer. So there's some amount you need to pull down to sort of compensate for the overestimate so that you can gradually converge downward.
And the 50% came out to be good based on your
Based on the
tests
tests,
as well.
yeah.
Okay. Thanks.
Praveen, Microsoft. So I have a question about the target loss rates that you talked about.
Yeah.
So you never mentioned the numbers. Are you tuning them differently for different workloads, or?
Right. I think it's going to be subject to tuning and further research and discussions. For this particular iteration of BBR v2, we're targeting a loss rate around 1%. So currently the threshold at which it backs off is a 2% loss rate in that measured round trip time. So that the overall net effect, since a given flow is only going to be probing for some fraction of the time, is much lower than 2%. But that's the basic dynamic is we're setting a max at 2% to try to achieve an overall average well below 1%.
So if I understand this correctly, so there's no immediate reaction. The reaction is based on the rate over a period of time.
There's a once per round trip time reaction to ECN or loss. Yeah.
Okay. I have a follow-up question to the 50%. So to measure the RTT. Is that
Praveen,
50?
I'm going to interrupt here because we have about 1 or 2 minutes left and we have several people in the
This
queue
is
behind.
really quick.
Okay.
So 50% of BDP or 50% of the current sending rate?
50% of the estimated BDP.
Just for the folks in the line, I'm going to cut the line now, and please keep it quick.
I'm happy to talk after the ICCRG session too.
Lean's around.
Michael, I was curious about the data center TCP style ECN mechanism. Are you negotiating accurate ECN, or how are you getting your feedback?
For right now, we have internal to Google, we already have a private negotiation mechanism, and we're happy to work with people on the public efforts to negotiate a TCP style mechanism, such as L4S, something like that. But right now, internally, we have our own negotiation mechanism, and externally in the public internet, since there is not a standard, we're not using it yet in the public internet.
Okay, thank you.
Jake Holland, I was wondering about the probe bandwidth. I think you said it responds to loss in ECN, but I don't think I heard you mention RTT. Are you also responding to increase RTT?
Yeah, I forgot to mention that. Yeah, so I think I mentioned it in the slide, but I forgot to say it out loud. But basically, as before with BBR, if we essentially see an increase in RTT, but more specifically, if we see a what looks like an in-flight that is basically 1.25 times the estimated BDP, then we've estimated that we have enough of a queue, that we've probed enough, and it's time to drain and move on.
Andrew McGregor, I have a excuse me, I have a pretty good idea how you would do this inside Google, and that you would, but on the public internet, would you be proposing to set the ECN and loss rate targets as a function of the serve code point that you're sending on?
I don't know about diff serve code points. Yeah, I don't know. We could talk about that offline.
Yeah. If you haven't thought of doing it on Google's backbones, you really should, because that would fix some things.
Jonathan Morton here. I don't know if you saw the some congestion experience talk on Monday. Sorry. But do you think an SCE would be a useful mechanism for improving the ECN fidelity in terms of BBR?
I think it would be better than no ECN style signal at all. Yeah, I think my guess is any form of ECN signal that gives you a fine-grained picture that sort of more than 1 bit per round trip time. I think any sort of more detailed ECN signal I think would be useful. Yeah.
Okay, I'm sure we can discuss this in more detail later.
Yeah,
on.
absolutely. Thank you.
Thank you so much, Neil. And please find Neil outside for more discussion. And hopefully we'll hear more about the results of your BBR-V2 experiment, perhaps on the list as soon as you have something to share. But, thank you so much. And now we move on to Payman.
Okay.
Take it away.
Thank you very much. Hi, everyone. My name is Payman Taimouri, and I'll be talking about how to make ECN more useful. So let's see how. First, I'll discuss about ECN. You already know about this, but just a short introduction about the issues that we see on using ECN. And then the network utility maximization framework and how we use ECN in this framework. And some simulation results and model validation and the benefits that we get from this. And we will discuss some applications and the advantages of using ECN in this framework. And I'll conclude my presentation after that. So you already know about ECN and how TCP uses ECN based on an instantaneous queue that marks packets above a threshold, and it interprets like a marking probability per RTT, and based on this probability, it cuts the window, congestion window. It doesn't have the window as in TCP, but it cuts a bit less than TCP and like oscillates more, but in a shorter scale. This is how it gets its benefits. But about the issues with the ECN, if we interpret it as a 1-bit information, so there's no problem with normal ECN, how it is defined in this RFC. But we only get one signal per RTT, so it's like too little and too long. But if we use DC-TCP style marking, so for example, in DC-TCP says that if the marking probability is low, it diminishes the usefulness of ECN. And also, it's useful only when it deals with packet dropping, not just marking. So it's better to keep it a bit higher and get a better signal out of the network about how much it is congested. So it's better to use a higher marking probability in the network, but the problem is that this is not an additive measure, it's multiplicative. And also, it has problems with using in the theory, like the norm theory, because the theory works with an additive cost or additive signal with the network. So as a short overview of the theory, network utility maximization deals with solving a rate allocation problem based on some constraints in the network. So the goal is to maximize like social welfare in the network subject to some constraints. And in the simplest case, these constraints are link capacities. We don't want to exceed link capacities, but we want to increase send rate of each source as much as we can until everybody is happy. So this is how this maximization problem is defined. So in this case, UR is the utility function of each sender or source R. This utility function represents the happiness each source has, or how much happy each source is by sending, for example, at rate XR. And link capacities, which are denoted by CL here. And the crossing traffic on each link, which is denoted by YL, shouldn't exceed the link capacity. So this is the simplest case that we can represent this rate allocation problem. But what happens if we use ECN and with this theory? The problem is that if we have higher marking probabilities, as we have, for example, in data center TCP, and the plot on the right side shows that data center TCP with different BDP can reach to higher marking probabilities. We have the problem on the plot on the left. The two equations here, we plotted the deviation that these two have. The deviation shows that if the marking probability in the network increases, the deviation is larger. So we have like an estimate bias that should be removed in the theory, because the theory works only with sigma, but the signal that we get from the network is the first one, which is multiplicative. It only works if the marking probability in the network is much lower than 1. It's, for example, close to 0.05, 0.04, or some numbers in that range, not higher. But we see that in data center TCP, as shown in the right plot, which is plotted by some equation about the theoretical marking probability with one bottleneck link and the number of competing flows. We see that it's at least around 0.16 or close to 0.2. That's a problem that we see with using ECN, that we cannot use higher marking probabilities, although they are useful in the network. So what we did is that we turned ECN into an additive signal. Actually, we played with the theory and somehow it was extended to adopt this. And we used red because we wanted to have a deployable solution, not something which is hard to redeploy. And it's just a matter of configuring red in commodity hardware. And as benefit that we get faster convergence, because with higher marking probabilities, as we will show in the rest of the presentation, we see that we have a faster convergence because we get more signals from the network. It's a more fine-tuned signal. It's not just 0, 0, 0, and then after a while 1 as a signal which shows that the network is congested. So if we get a more fine-tuned signal, then we can have a faster convergence. And it could be used actually to have earlier feedback with virtual queues, and we probably can start marking packets even below the capacity. I'll skip the theory, so just as to show how it looks like. There is a theorem on solving maximization or optimization problems with some constraints. It's called KKT theorem. The first condition here is the original theorem, which shows how it works. It has two variables here, mu I and lambda j. What we did was that we changed these with two functions, here f pi and k vj. So it has some proof that you could find in the technical report that I cited on the first slide. And as the function that we incorporated in the theorem, we used this function, which is a logarithmic function. And we derived a new Lagrangian function, which is the base for deriving three types of algorithms, a primal, dual, and primal dual, depending on how we divide the controller between the sources or the network. As a simplest case, we use RED as we talked about. We use RED as the dual algorithm. So the algorithm is on the top. It shows that the current marking probability, marking probability at time step n or iteration n, is the backlog, the current backlog, divided by some maximum threshold. And it's limited to the range 0 to 1 because marking probability shouldn't be larger than 1. So how we can achieve it is easy, but just configuring RED. So we set a mean threshold to 1, max threshold should be actually larger than some number, which is derived by a stability proof in the report. For example, to have a notion of this number, if in a scenario that we simulated, we had a BDP close to 1.7 megabytes, and in this case, alpha is some bound on some function of the second derivative of the utility function. L is the maximum path length in the network, and S is the maximum number of competing flows. So in that case, we had a max threshold larger than or equal to 1.3 megabyte. But what we did in the simulation was that we set this number to a smaller value, but we didn't observe any instability. And also the average queue size in that case was around 75 kilobytes, much lower than BDP. We also set the max P to 1 because we wanted to use the whole range of marking probabilities from 0 to 1. And also WQ to 1 to have instantaneous queue marking. We didn't do this like exponential smoothing and the queue size. So this could be achieved by just configuring RED in commodity hardware. And as one of the actually benefits of doing this and using that function that we showed before is that we could remove the bias that higher marking probabilities has on the actually the rate that each flow gets. For example, in this case, we have like a parking lot topology. We have a number of 5-hop flows competing with a number of 1-hop flows, like cross traffic. So N1 and N2. We did a simple simulation with data center TCP. we actually, instead of the end-to-end marking probability that data center TCP works with, we use this function. So we see that in the simulation, the rate actually that each flows gets, 5 hop flows divided by the rate that 1 hop flows get. Actually, the ratio doesn't change as the number of 5 hop flows increase. This means that as the number of 5 hop flows increase, we have a higher and higher marking probabilities, but it doesn't affect the behavior of the controller. So that's the good point about the theory. And we derive some other optimization algorithms. The first one is a primal one. It's similar to the one that Kelly had in his paper, but if you remember, we have a different cost here, which is a logarithmic function based on the marking probability that we get, end-to-end marking probability, but in Kelly's algorithm, it's just cost. And also two different dual algorithms, but they need actually implementation in routers. Probably people might say that they cannot be deployed, but to have a full set of algorithms, we derive these as well. And also a combination of these that we could have to have primal dual algorithms. So we validated all of these algorithms here with a logarithmic utility function. This function, as one of the properties of this function, we should have actually proportional fairness. So in this case, 5 hop flows cross 5 hops. It means that the rate should be 1/5 of the 1 hop flows. So the left plot is a numerical evaluation with mathematical. We see that the line below, the purple one, is exactly 0.2. It shows that for every number of crossing, every number of 1 hop flows, it means that this ratio or the theory is not affected by the number of competing flows and also the marking probability. So it means that the theory was successful in coping with this ECN usage problem. But if we don't use that, you see that as the number of flows increases, we have more and more deviation with this rate ratio. And the right plot is simulation with Omnet, and we see that they are pretty close to 0.2. Some applications, we actually can obtain utility function of controllers when the marking probability is not low. So as one of the benefits of this. But in the literature, probably you have seen that this is approximated by some of the marking probabilities and conditioned on being the marking probability being low. But in this case, with this theorem, we can use this to obtain the utility function of the controllers with higher marking probabilities. And also we can inflate, deflate marking probability. We can play with it. And by marking probability, I mean the equilibrium marking probability, because there is a base in the log function phi, and we can play with this to have different marking probabilities in equilibrium. So that's also useful. And you are not obliged to have a fixed marking probability depending on the behavior of your controller, but you can have different ones. And we can see in the next slide the benefits of playing with this. And also the potential to deal with virtual queues. We have two scenarios here. We have a link with 1 gigabit per second bandwidth and also a limited link. on the left, there are two plots. The steady state short-term fairness, we see that as we increase this base parameter to get higher and higher marking probabilities in the network, the flows behave smoother and smoother. And also when a new flow joins, because we get more marks from the network, it's like more fine-tuned and more signals received from the network, we have a faster convergence rate. And also on the left side, we limited the bandwidth to see how much we can increase the marking probability and does the theory work with this or not. We see that it works up to, for example, 0.99 marking probability, but we see that because at that, like in this case, we get all ones from the network at some, and at some time we get 1, 0, then we lose some benefits from it. So it's better to have a high marking probability, not so high and not so low. So that's the benefit that we can get by playing and increasing phi, not too much, to have a marking probability in the middle of this range. But although it can work with low and high marking probabilities. To conclude, we tried to improve ECN to widen its range. We didn't want to limit the range to be too low or maybe too high, because modern controllers like data center TCP and as I just heard about BBR-V2, because they use this ECN, DC TCP style ECN like method, they can have higher marking probabilities, and it's good to play with it to have faster convergence or a smoother behavior and get more signals from the network about the congestion, and also the possibility of marking even below the capacity. And as next steps, we will focus on experiments, because it was numerical evaluation and simulations, and also on deployment issues of this method. Thank you.
Hi, Jake Holland. Could you go back 2 slides real quick?
To which one?
One more. Yeah. What are those error bars? Is that like variance across experiments within a window, or what?
There are 10 different runs.
Okay.
The lines are the average, and the error bars the minimum and maximum.
Okay, thank you.
Hello, Jonathan Morton again. Existing ECN deployments use the low marking probabilities as DC-TCP style marking has its own problems with deployment, I think. But what would you think about an SCE, some congestion experienced, using the extra code point?
You mean using ACE?
I mean using ECT1 instead of CE.
Okay.
Because I think that's a way of getting the higher marking probabilities that you rely on here, without breaking compatibility with existing TCPs.
Yes, actually, the theory just theory just says that if we have higher marking probabilities, so it doesn't matter if you get it from a DC-TCP style AQM in the network or if it's from something else. As long as you have a higher marking probability, you can use this.
Mm-hmm. We have some prototype code which produces the SCE marking using the DC-TCP style of trigger. So we can have a ramp function over a small range of queue depth, for example, or a threshold function at a particular queue depth. And I think that's what DC-TCP style thing is what you have in mind.
Yeah. I think you can apply this theory on what you already said. It doesn't matter if it's only DC-TCP style or something else. But we only tested this with DC-TCP style marking. But we believe that it works with that case as well.
Yeah. I think it's just something to bear in mind with your planned experiments.
Yeah. Thank you.
Hi, Bob Briscoe. I just posted a mail on the list pointing to another way to get your additive property within the number space 0 to 1 by essentially you, instead of altering the network, you alter the end systems. You transform the number space from p to p divided by 1 minus p, and then so it's essentially taking instead of the number of marks divided by the total, it's the number of marks divided by the number of unmarks, and then it transforms the whole space, and you get your additive property in a transformed number space. So
the marking probability is the same as the way the TCP computes it. Is exponentially smooth. Just the logarithmic function, you mean?
When you're reading in the marks,
yes,
you just calculate the fraction differently. You don't use the total number of packets. You use the total number of unmarked packets, and then you sort of compress the number space into 0, 1, your additive number space.
Yes, it's like something like that.
Any more questions?
Michael, that's another question, a clarification. I'm not sure if that was a misunderstanding or not, but just to be very clear, this calculation is done in the end system. Also the way it was presented, it's done in the sender. So it's just a regular RAD with this slightly weird configuration, but other than that, everything is calculated in the sender already in that. So it's yeah.
Yeah. Thank you.
All right. Okay. Well, thank you so much, Payman.
Thank you.
Who's up next? Bob, you're up next.
Thank you, everyone. All right. This slot was going to be Joachim giving an update on paste chirping, but he's fell ill and had to go home. So I'm going to give an update on the implementation status of TCP Prague. Yep, thank you. And just for those, I actually don't think we need this, given the last 3 talks have been about this, but essentially TCP style is the where we're trying to get to with more tinier sortie, so you get high utilization and low queuing delay. Just a quick update on the implementation status of all the bits of L4S. And in fact, I guess we could say that what I've just heard about BBRv2, I was hoping that I wouldn't have to do the fallback part of TCP Prague to deal with all the lost stuff. And it seems like we're very much converging on all having the same pieces with BBRv2 using the TCP style bit for the when it has got ECN, and so it looks like that you could call that an implementation as well, but I don't want to sort of co-opt it without looking at it further. But anyway, so yeah, now Linux implementation of the network part. There's a TCP Prague implementation, a Quick Prague implementation, an implementation of the real-time adaptive screen for L4S, and all the bits of accurate ECN as well, which anyone can use separately from L4S. So, and in particular, I just wanted to make people aware of an announcement I made in the Transport Area Working Group that DOCSIS 3.1 will support this DCTCP style ECT1 behavior as part of the new specs that were released in January with mandatory L4S support, and there's also reduction in the request grant loop in the Mac, but that's not really for ICCRG. What I want to talk about here is how the internals of TCP Prague and what we've been doing on that. it's based on data center TCP. So if you know that, you're in good shape, and there's just a few deltas. There's the URLs for testing it and how to enable it. It's now ported up to the tip of the Linux tree. And what I want to talk about today is all the parts we've had to add to DCTCP to meet the what we call the Prague L4S requirements that were agreed here in Prague in July 2015. We've renamed them from the TCP Prague requirements because they're not just for TCP. So we have now an implementation of this congestion control in Quick. It's very early days. I mean, it was only built on Saturday. So, but it took a day and a half to build. You know, most of it was already there. It was just a very small change to the Reno algorithm. Yeah, which is good news for Quick, if you like. You know, that it's easy to do these things, assuming it works. That is that. Or assuming it works once it's been fully tested, I should say. It's been tested a little. Here, these are all those L4S Prague requirements and where we are with the implementation of them. I'm not going to go through this slide now because I've got it again at the end. I just wanted to say this is where we're trying to get to in this presentation. And what you will see though is that about half of the requirements are met by altering the base TCP stack in Linux. And a good half of the remainder, in other words, a quarter, are back portable, if you like, to DCTCP as well. But that's up to the DCTCP maintainers, obviously. So I'm going to skip this slide. I had it hidden, but I guess this is the PDF set. I didn't realize that was going to happen. Just because otherwise it's going to take too long. And I'm nearly going to skip this slide except to say that the accurate ECN implementation, there's one little extra bit on the bottom there which we've added to the Linux version for testing, which allows you to force the other end to give you fine-grained feedback even if it doesn't support accurate ECN. So if it's a classic ECN receiver, we can certainly for testing, I'm not sure I'd advise this for production, but it essentially sends CWR all the time to the other end, which means that whenever it does an ECN mark, it then immediately turns itself off, so you don't get a whole round trip time. And it also tests for a bug in BSD as well before it does that, which would otherwise give you no marks at all. So moving on, fallback. Now, I need to make it clear that fallback on loss, this is what I would say would satisfy a RFC 5681 zealot. So, you know, this is if you want to keep absolutely to the RFCs, that's what we'd do. I'd quite like to fall back to something more like BBR, as just described, and I think now you could think of the two as synonymous. Depending on, well, BBR's loss, the answers to Praveen's question I'd like to hear about. But anyway, moving on. The fallback on loss to be 5681 compliant, what we realized is that, well, partly 4 years ago, we realized that there was a bug in Linux that didn't fall back at all in the DCTCP Linux, unless you had a timeout. But if you had a fast retransmit, it didn't even notice it. We patched that 2 years ago, but it didn't go through. So we've patched it again, and we've certainly patched it in TCP Prague. But what we want to do for the future is at least not overreact by halving and also having an ECN response. So the idea is to, as you can see, and where's the little right on here? Yep. As you can see here, the ECN and the loss responses are fairly independent. So you've got the sort of EWMA being calculated. This thing called alpha is the calculation of the weighted moving average of the ECN signal in DCTCP. and that carries on independently. And if there's a loss, you sort of get a round of dealing with that loss. And then when it comes back, alpha's carrying on without having been affected by it, which is different from how the current code is. And the other thing is we've reduced the amount of loss so that when it's compounded with the reduction for the ECN, they come to a half, rather than doing two reductions in for both signals, which is what you see there. Let's move on, because that's more in the 5681 world. Right, the next one, which probably more relates to what Jonathan Morton was talking about, fallback Torino friendly on classic ECN. This is the next requirement. And essentially you've got this flow diagram over here where if you get an ECN mark, is it from, first of all, is it from a L4S AQM or a classic AQM? And if it's a classic AQM, is it a FQ one or a FIFO one? If it's an FQ one, it is protecting everyone else from you anyway, so you don't have to fall back to the Reno behavior because you're in your own queue. So the only case we really need to worry about is this FIFO one here. And on all the or in all these studies from the academic world, including our own, and I'll call that academic because I was in Similar at the time, the ECN marking level found on the internet seemed to be virtually near zero. And in fact, I think the latest one that's unpublished that Brian Trammell told me the other couple of days ago, I think he found 13 CE marks. 16. Right. However, I've got a suspicion that all those studies are wrong because they're not they're active studies. They're sending traffic that isn't big enough to congest the link. So they're only finding the background level when they send traffic. Whereas the Apple data is looking at the traffic all the time. It's passive. And so they're much more likely to find cases when it becomes congested. This is a picture of a slide from Padma Boomer from March 2017, this black one, which showed that they were seeing some CE marking in certain countries, and particularly the Argentine Republic, at 30%. But when you just look at that figure, that 30% marking, right? But it's not. It's 30% of Apple devices saw at least one mark in 12 hours, right? So that's not saying it's 30% marking. And Padma says that was the signature of that traffic looked like ECN marking. You know, it wasn't just something that was maybe diff-serve mangling or the rest of it, but it was mainly seen on the uplink, and we haven't got any data yet to dig into that to find out whether mainly means nearly always, and possibly when it was on the downlink, it may have been marked on the uplink from someone else, you know, like a peer-to-peer flow. Because then that determines whether we're in the always in the FQ side of this flow diagram here, and therefore there isn't a need to deal with this FIFO case, or whether there are actually maybe someone's turned on some old Cisco routers with a FIFO queue and ECN red or something like that. So that's that one. That was also a hidden slide. Right, this is a copy of a slide I showed in the AQM working group when it existed, to show that when you remove the queue from, when you have such a small queue because you've dealt with it using AQM and a DC-TCP style congestion control, you actually get a situation where you start hitting TCP's minimum window of 2, which is built into the specs and the code, because you lose the ACK clock if you go any lower than that. And as you can see from this, just 5 flows in this region here, this plot shows the range of possible capacities and the range of possible round trip times, and typical broadband is in this range and typical data center is here. And anything below the line between red and green there is potentially in a CWIN less than 2. So effectively what happens in those regions is when you've not got a queue, TCP can't go below 2, so it's effectively become unresponsive because the AQM is telling it go lower, and it's saying, okay, I'll go lower, and now I'll round back up to 2, and then it forces the queue to build because it's not going lower, and so it forces a larger round trip time by forcing a queue, even though the AQM is telling it not to. So we wanted to try and solve that problem by fixing TCP so that it can go below 2 and can go below 1. And so far, managed to do it for Reno. We've still got a synchronization problem when we do it with DC TCP that we're trying to fix, but this is with Reno. And it's uses pacing. You sort of have to, if you're lost your ACK clock, you have to send a packet less often than you're getting ACKs back, so you can't use the ACK clock. And we use a rather than an additive increase of 1. The other problem we've got is that when you go below 2 or 1 as your congestion window, if you still use an additive increase of 1, you're aiming at, say, half a segment, but you keep adding 1, and so the additive increase is too great for the thing you're trying to aim for. So we've got this sort of scaling. Every time you change SS thresh, you change the constant that you add for that until you next change SS thresh. So it's sort of like an additive increase, but not a constant additive increase. You modify the constant depending on what region you're in. Anyway, you can see it's working on the right here. Here you've got all the congestion windows of a number of flows, and the right-hand side gives you the congestion window in segments, the left in bytes. So you can see you're working below the 2 segment previous limit. It's working very well, but as I say, we haven't yet got it working with DC TCP, and it's something to do with the way we're doing the EWMA, which also has to be adjusted for. It's calculated every round trip time, but we're not getting a packet every round trip time because you're sending your round trip time is so small. You're sending less packets less often than your round trip time, and so we have to do the calculation of the EWMA adjusted for every time we get an event of an ACK coming in, and something's not right about it at the moment. Anyway, I won't go into that here because I don't need you to debug our problems. I was going to jump over that. Right. The other aspect of TCP Prague we wanted to do was make it perform better. There's 3 slides on better performance. First one is to be able to send ECT on the control packets, particularly the SYN. And there's a draft in the IETF to do that, and we've implemented that. No, DC TCP implements that already. The issue I want to raise here is that when you do that on the public internet, we found from a measurement study that 84% of servers turn off ECN when you send them a SYN with ECN on, which didn't help much. And what I mean there is that normally ECN is negotiated at the TCP level, if it's TCP. But if we set ECT in the IP header while we're trying to negotiate it in TCP, it turns off ECN for the rest of the connection. And that we trace back to a patch that was put into the Linux servers, and I understand it's not in Windows, which is good, and that probably explains the 84%. That patch was put in 2012, and we have submitted a patch on that patch to make it specific only to RFC 3168 SYNs. So if you're sending an accurate ECN SYN with ECT on the code point, all the install base of Linux servers will not turn off ECN anymore once that patch has been backported. It's a one-line patch, so I'm hoping it will backport fairly widely. And that is actually the patch. Basically, we're just checking more of the TCP flag bits than are currently tested in the patch, in the previous patch. So the patch of the patch tests for the zeros as well. Right. Finally, there was a talk on pace chirping to get up to speed faster. That's particularly relevant when you're using DCTCP style feedback and DCTCP style marking. When you've got such a shallow threshold, it's really difficult to get your slow start under the threshold because just a few packets and you can hit the threshold, get an ECN mark, and then you pop out of slow start. Now you could just say, well, let's start averaging the ECN, but you don't know what sort of ECN it is, and you don't know whether the ECN is coming from the same bottleneck as where you're getting delay from. So we use only delay. And one of the extra bits we've done since last time, so I've just gone back. So we got very fast startup without overshoot for the initial slow start or slow start after idle. We've been thinking, well, how can we implement that when you, in the middle of a flow, suddenly want to jump up to a new amount of capacity. So say your two flows in a link, the other flow stops, and normally Cubic takes quite a long time to get out. And in fact, typically Cubic will take hundreds of round trip times before it attains that new capacity if it's in the middle of congestion avoidance. And so what we do, we use the property of DCTCP that was on the previous slide, and I will go back to it, that you get a regular frequent amount of marking with DCTCP, unlike something like Cubic. And so you can tell when it stops very quickly. It's like, if you're beaten on the head every 2 years, it takes many years before you realize someone stopped beating you on the head. But if you're beaten on the head every few seconds, you know when it stopped within a few seconds, right? And so in this case, took off a capacity limit. This was a simulation. And this was because Joachim became ill, so I've had to go back to his last simulations. Just took off the capacity limit as if a flow was leaving. And you can see DCTCP, because it's got the additive increase, takes, what's that, 60 seconds, so that's 600 round trip times. Cubic takes 150, 15 seconds, 150 round trip times. Ignore the BIC. And the one modified with pace chirping gets up there in 7 round trip times. And the queuing delay is still under 1 millisecond there. Whereas the Cubic, even though it takes a lot longer, is 150 round trip times, but it causes 20 milliseconds of overshoot. So much faster to get up there and much less overshoot. All right. But this is research. I'm not saying this is production ready, because it's got to work in Wi-Fi environments and all the rest of it. This is all fixed Ethernet. But it looks very promising. Right, so coming back to this slide that summarizes everything. We've got a few bits and pieces now in the mainline kernel, although most of them, a large part of the parts of TCP Prague were already there, and it was just really a sort of mandatory configuration of all the bits. So the dark green parts, if you're red-green colorblind, if you're red-green colorblind, the bold ones are for the green ones. They're in the main line already. This is Linux. The one I mentioned about scaling down to a window below 2 is, it's in progress. That code's not quite ready to release yet, so that's in a sort of private repository. The reducing RTT dependence we've presented here before. Still, we've only simulated that. We haven't put that all into the framework. And this is the one I mentioned where we're still wanting to see whether that Apple data shows us anything that means that we may not have to do that. Because that's just going to make things unnecessarily complicated in the code if it's not actually needed. So that is all. Just a quick one on performance. I showed this in TSVWG, but I'll show it again. How are we doing for time? Yeah.
Oh, hang on.
Okay. This is the last slide anyway.
Yeah, about 8 minutes left. Yeah.
Pardon?
Yeah, about 6 to 8 minutes left.
Cool. That gives a bit of question time. So this shows a complementary cumulative distribution function with a log scale, so you can see the very low levels of queuing delay at the higher percentiles. So the 5 nines percentiles here. And the reason for that is we want to be able to have real-time media in this queue. It's potentially a FIFO queue. So this is showing all the traffic in that queue and what it does with the DC-TCP one is that blue one. These are all paired, so like the dual pi 2 is the blue and red one, the FQ coddle is the green and purple one, and the pi is the and so all this traffic isn't there at once. For the dual pi 2, those two are together. For the FQ coddle, those two are together. And for the 2 pi ones, those two are together, because you can't have more than one AQM in a queue at the same time. So it's overlaid just for comparison. And the interesting thing is that the classic queue of the L4S, with cubic in it, is roughly a similar performance as all the other, what you might call second generation AQMs, the Pi, the FQ coddle. So we're doing no harm to existing traffic. And then the L4S queue, at the median, you've got 1 to 200 microseconds, which is confirmed by what Neil showed. He was getting similar queuing delay, but I think yours was in an FQ system, wasn't it? Yeah. Pardon? Oh, was it? Okay. Oh, so when you said coddle, you meant coddle, not FQ coddle. Yeah. Yeah, cool. And 99th percentile, 1 to 2 milliseconds, and so on, up to 8 milliseconds there. But the important thing to notice about this is, this isn't just a single flow. This is 300 web flows per second hammering this thing. It's 120 meg link, and there's 300 per second in the L4S queue and 300 per second in the classic queue, plus 2 long-running flows with these various traffic characteristics. So this is showing exactly the same thing that Neil explained, really, and this is the sort of philosophy of both DC-TCP and now BBRv2, that essentially you're keeping headroom when you've got a lot of traffic coming in and out, and DC-TCP does that by its EWMA, so it sees the general background level of marking, and a long-running flow will get out of the way enough for all the small flows to get in. But if there aren't any short flows, or there aren't any slow starts, the longer running flow sort of pulls itself back up and increases the utilization to 100%. So I think the intuition for them both, even though BBRv2 is a model-based one and DC-TCP is more a deterministic algorithm. Well, they're both deterministic. That's not a good way to. I don't quite know how to describe the difference, but they're essentially I think the intuition is the same. So that's cool. I think we're starting to converge. So summary, we've got very good performance and TCP Prague, and I'd be happy to fall back to, if I have a look at BBRV2, if we can maybe have a bit longer to look at it, maybe falling back to that is the way to go. Or you could look at it alternatively as BBRV2 uses DC-TCP, so it's falling forward, or it depends which side of the fence you're on, whether you're falling over one side or the other. Yeah. Cool. Finished.
All right, we have a couple of minutes for questions, but Jabber first.
Hi, Rob. So DevTech has 3 points from Jabber. One is a very good assumption that the CE marks from France are due to Free.fr's enormous 3 million plus deployment of FQ Curdle across their DSL subscriber lines. 2, he has no idea about Argentina, but OpenWRT is big there. 3, the BBR currently caps congestion window reductions to 4, unlike Reno. And he says, as for point 1, all someone looking at the data has to do is pull out the IP addresses related to Free.fr's BGP AS. That's it.
Yeah, and that's actually the conclusion we've come to, that we need to look at the CDN side rather than the end system side to try and get this data.
Praveen, could you expand the status page for the implementation?
Yep, I'll go back to that one.
Yeah.
Yep.
So detecting loss in units of time, is that suggesting that we only detect in units of time, or also with packets?
Yeah, what I realized on that is that the existing rack implementation, as long as you pace your initial window, that meets the requirement we need. It's then effectively, implicitly working in time, even though it's still doing the 3 pack rule, because the packets are spaced in time.
Okay. Yeah. Right. The other question I had is ECN capable TCP control packet. So it seems to be default on for DC-TCP and default off for Prague. I'm a little bit confused on why.
Yeah, sorry. I jumped over that slide because I forgot to make that point. The reason it's default off, that's just at the moment, just because we haven't written all the fallback code. And so until we've written all the fallback code, we'd rather have it off and you manually turn it on if you want to use it. And then once we've written the fallback code, we can make it default on. Yeah.
Hello again.
Can I guess what you're going to talk about?
Well, it has to do with the classic ECN bottleneck, of course.
I will say, let's keep it quick though, because we have only a minute.
Okay. I'm mostly looking at your data saying that ECN is rare. I'm wondering if that could be due because ECN is really.
Where are we? No, I'm not saying it's rare. I'm saying that the data that said it was rare is wrong. That the Apple data is the one we've got to look at.
Okay, I'm cutting the mic here, and let's go through this because we basically have to move on to the next talk.
Fair enough.
You can ask quick if you
just very quickly. I'd presume, given that you're working with Cable Labs, that you've looked at aggregating MACs. I don't see anything in the presentation about it, but it would be nice to see that, especially for the Wi-Fi cases.
Yes. Right. Okay.
So
that's a large element of what we've been doing, and maybe I'll talk offline about that. Yeah.
So one question: so when RAC now in the latest iteration has the 2-pack rule in there, and the rate just goes high enough, then you're basically reducing or shrinking a reordering interval in time again,
not if you pace your initial window over your round trip time.
Yeah, but eventually the rate goes high enough.
Well, no, but if you've got a certain amount of packets paced over a round trip time when you start, that's all, and then later on when you get your reordering window sorted out, you're okay.
Okay.
Yeah.
All right. Thank you so much, Bob. And Sylvester, you're up next.
Can you hear me well? Seems so. So I'm Sylvester Nádas from Exxon Research, and I would like to present multi-timescale branded profile and its application for burst-aware fairness. So what is this whole thing about? We give a definition of fairness on multiple timescales based on bitrate measurements on multiple timescales. And we give an implementation. We build on core stateless resource sharing solutions, and we only update the edge marking to reflect the timescales in the marking. And we show potential advantages and characteristics. It is based on fluid simulations, assuming ideal congestion control behavior, so instantaneous convergence, basically. But we don't use the congestion control fairness itself. It's enforced by the core stateless resource sharing. And we compare our results to two-rate 3-color marker, TCM, as a reference. So bitrate measurement and timescale. So bitrate is a derived measure, and you have to translate discrete packet arrivals to bitrate. And it always has to have a timescale associated. So it's basically volume divided by time. And there are natural timescales, like RTT, like 1 second, like some kind of session duration target, maybe 1 minute, 10 minutes, months. Most of the time today, mainly 2 is used, RTT and the most again. In fairness. So how can we have fairness in multiple timescales? When we measure bitrate, and when we measure bitrate when the source is active, we use it to describe performance. But we can measure bitrate during both active and inactive periods to judge the fairness of the resource sharing themselves. So if you want to have some kind of fairness in multiple timescales, we can balance all the timescales and consider all the timescales. And we can allow higher share on shorter timescales for flows below their fair share in the longer timescales. So you can see there are 2 examples. One, when we have the same fairness on all timescales. We have a yellow flow and blue flow, and the yellow flow is transmitting for a longer time. So naturally, when the blue flow is not transmitting, it will get the capacity. So it has 5-to-1 resource sharing on the long term. But even in the shortest term, they have 1-to-1 resource sharing. So the download of the blue flow takes quite some time. But if you take into account the history of the blue source, you can allocate higher capacity to the blue source temporarily and have improved throughput for the blue flow while having basically the same throughput for the yellow flow if you measure it for the whole download time. So what is core stateless resource sharing? There's an example for that is per packet value-based core stateless resource sharing. So it's a framework which allows a wide variety of detailed and flexible policies. It enforces these policies for all traffic mixes and scales well with the number of flows. We have quite an amount of publications about this. But shortly, there is a packet marker in the edge. Somehow, yeah. So there is packet marker in the edge. And there are resource nodes in the core of the network. And the packet marker encodes all policy and actually flow information into a single value marked on each packet. And the resource node can base its behavior on the packet marking only. It has no need for what the policies were, which flow is it, or it doesn't need separate queues per flow. Maybe it might need separate queues per delay requirement, but definitely not per flow. So you do the same thing if you have a single flow or if you have 1 million flows. And there are very fast and simple implementations there. So the simplest core stateless marker is pretty well known. It's a 2-rate 3-color marker. There is actually a drop eligibility bit there, which can be set to false for committed information rate. That is usually something like guaranteed traffic. And there is an amount of excess information rate allowed. It can be up to the link speed. And these packets are allowed into the network, but we don't say anything about guarantees at all. The only thing we do is that we allow it into the network. And then it basically depends on congestion control aggressiveness, for example, which flow will get which amount of capacity. And of course, we can drop some packets there. So how can we extend it? We can increase the number of drop precedences. So instead of having a single seer and access information rate, we can have more rates, and we can control the resource sharing more along those rates. Some core stateless proposals have here can have hundreds of rate and have a really well fine-grained resource sharing among flows. But you can also increase the number of timescales. So you can have, for example, if you take this bucket-based approach of TCM, you can have more buckets per drop precedence. And in an example I will use in the rest of the presentation, we increased the number of drop precedences to 4, and we increased the number of timescales to 4 also. So this is the example. We call it multi-timescale bandwidth profile MTS BVP. So we have, again, 4 drop precedences and 4 timescales. And there is a matrix setting the rate parameters of this. So we have rates associated with all of these token buckets, and we have maximum bucket sizes calculated from timescales. So maximum bucket size is around the timescale multiplied by the rates. It's actually slightly more complex, but this formula is much better for understanding this. And how we decide whether we can mark a packet to a given drop precedence, we check all of the token buckets associated with that drop precedence, whether there are enough tokens in these buckets, and we decrease, of course, these buckets and marks the packets accordingly. And we do that with all drop precedences. So we have an example scenario for access and aggregation network. We have 5 nodes. We have a common bottleneck, capacity of 10 gigs, and the long time fair share of the nodes is 2 gigabit per second. There are several flows or users in one node, but there is only a single bandwidth profiler, and we want to enforce fairness in this case, in this example, among these nodes, not among the subflows of the nodes. And what advantage are we looking for? We want to have nodes with good host history to access high portion of the bottleneck capacity temporarily, as long as they have good history. So for example, high peak rates achieved for small bursts. So it's for those small bursts, for those nodes which have good histories, it feels like an underloaded system even when it is overloaded. And at the same time, we want to maintain the multi-timescale fairness we defined. So as I said, it's defined by a matrix. I won't go into the very details of this of the design of this matrix. So these are the token buckets. This is the matrix and the timescales. But I will highlight some of the design features. There's a link to our paper about this, and you can find the exact algorithms there. So what we can do, we actually want to guarantee some bit rate on different timescales. So DP1 is dropped last. So by these bit rates on different timescales, you can set which bit rate is guaranteed to a given node. Then you want to have a throughput target for small and medium files in nodes with good history, and some kind of throughput targets for nodes with still reasonable history. So DP2 is dimensioned in a way that all DP2 packets go through when all but one nodes are having bad history. So you have a single node with good history. All the others are transmitting for quite an amount of time to achieve the state we call bad history. And then the single nodes the new node can reach these bit rates. And we want to converge to fair share on all timescales, including largest timescales. So we have this fair share of C per N in different places in the matrix. So what does a timescale mean? Timescales determine the bucket sizes on the same column. So for example, 2 seconds determines the bucket sizes on this column. And it also means how long the bit rates on the previous column can be maintained. So we have the first timescale actually set to RTT. And the other timescales are determined based on file sizes and based on definition of active period, when after this amount of activity, the node is considered high load. So a fluid simulation example. In this example, we have nodes 2 and 5 having a really bad history, transmitting for quite a while, and the red flow arrives to the system. So for a while, all his buckets are full, so he can reach this 6 megabit per second throughput. So it starts on timescale 1. And you can see in this timescale 1, actually the shades here are the different drop precedences. So you can see that at this timescale 1, only DP1 and DP2 packets go through. And after a pretty short time, it's 0.1 second here, it goes to timescale 2 and can reach only 4 megabit per second. And after that, its transmission stops. And the different flows have actually slightly different history and are changing timescales in a different way. But how actually DP3 is distributed among the nodes is determined by two things: the timescale of the nodes on that drop precedence and the number of flows, number of TCP flows. And an interesting thing here is that the high load nodes were much more aggressive, having tens of TCP flows, while the low load node had a single TCP flow. So on the same DP, we divided bandwidth based on the number of flows. So we have simulation advantages with this fluid simulator. We have traffic model, Poisson arrivals, basically two file sizes, small and large, and the maximum number of flows per node is also set. And we define here something called nominal load of a node. That is the load of the node divided by its fair share. So a low load node is having a nominal load smaller than 1, meaning it generates less than 2 gigabit per second traffic in this case. And the high load node is having nominal load larger than 1. And we also have a system load. So we named our scenario according to the number of low load nodes and the number of high load nodes. And we vary the low load node, the load of the low load nodes and the load of the high load nodes. So the system load, and we can calculate the high load from the above two. It's pretty hard to say low. Okay. So some selected simulation results. First, I have to mention that node throughput is measured only when the node is active. So the low load nodes are not always active because they have relative load below 1. So if you add up these numbers, you get more than the capacity, and that's the reason. And what you can see here is we have TRTCM as the reference case. So we have the scenario I've shown, TRTCM taking care of resource sharing, TRTCM only having SEER set to 2 gigabits per second, and AER can use the rest of the capacity. And we have the multi-timescale bandwidth profile matrix I have just shown. And let's concentrate on this too low, 3 high scenario when the low load was 0.5, and we increase the system load. And you can see that when the system load is below 1 or below 0.9, basically, there is a real, okay, what's on the figure? So it's again the node throughput measured when the node is active. The axes are the averages, and the top and bottom is the 10% worst and the 10% best capacity. And what you can see is that there is no big change when the load is small, but when the system load approaches 1 or is well above 1, the low load nodes see much higher average. They can often reach even the 6 gigabit per second we said. And this is a case when you have 2 low load nodes in the system. You can have similar but smaller gains when there are 4 high load nodes and the single low load nodes. And at the same time, for the high load nodes, there is not a big change. The biggest change is that actually the worst 1% goes below the 2 gigabits per second. But the average is about the same. Actually, the best 10% is better. So what you can experience here is that you have increased quality for low load nodes and almost no change for high load nodes. And based on results in the previous slide, we defined the measure called experience system load for low load nodes for multi-timescale bandwidth profile. And what is that measure? It's defined as the system load in the equivalent TRTCM scenario when the average node bandwidth for low load nodes is the same in that scenario, so in the TRTCM. So how does it look like? So what does, like a concrete number, 0.9 means here that we have a system load of 2 in this scenario. Again, 1 low load node and 4 high load nodes. We have a system load of 2, but the average throughput seen by low load nodes is as it was in the equivalent TRTCM system when the load of that system was 0.9. So what we can see here is that in all cases, basically shown here, the experience system load is well below 1. And if the load of the low load node is decreased, then this experience is increased. So an example here again, it's basically the example I have shown in the previous slide. 2 low load, 3 high load nodes, system load is 2. And the experience in that overloaded system is like TRTCM with load 0.8 for the case when the low load is 0.5 and 0.65 for the case when the load for low load nodes is 0.2. And like in a way, naturally, if you increase the number of low load nodes, it means that there is a single high load node generating very high system load, and that the low load nodes have a smaller percentage of traffic. You have even better performance. So if you have smaller load for the low load nodes, then it's better performance. So basically, the green ones are below the blue ones. That is because nodes with smaller load have good history much more often. And also, as I said, as you increase the number of low load nodes from the total 5 nodes, even at very high system loads, you experience very good experience if you compare it to the TRTCM. And why is that? That is because in TRTCM, access to extra capacity above the fair share was basically based on congestion control aggressiveness, and the high load nodes have a much higher number of flows, and they receive much higher share of that extra capacity. We actually did some preliminary packet level simulations. So this was an ideal fluid model. It's always a question whether it works with the real TCP. So we did NS3 DCA simulations. We have 5 cubic TCPs per node, and these results are showing 1 second sliding window average. And we had to scale down the speeds here, so it's a 100 meg bottleneck. But otherwise, the things are the same. And what you can see here is that there are these 4 greedy nodes having achieving bad history after a while. Then a new node comes, and it can reach this perfect history state for a while. And after that while, it goes to the good history state. And then after the 30-second period, basically, it will be equally having a bad history like the others. So there will be an equal resource sharing. So again, in summary, we gave a definition of fairness and multiple timescales based on the bitrate measurement on multiple timescales. Propose an implementation. The really good thing in the implementation is that you don't have to change the core part of the core stateless scheduler. So the scheduling remains the same. You only have to update the edge marking to take into account bitrate measurements on different timescales. And we have shown potential advantages and characteristics. You can find much more details about this talk, the article. Also, there is quite amount of work about core stateless resource sharing recently. You can find that there. That concludes my presentations.
We have a few minutes for questions.
I have a comment on that work. We have done similar stuff called APC, activity-based congestion management. And this work was motivated by re-ECN or Connex, because some years ago, with Connex, we wanted to achieve fair resource sharing in in a stateless network. And also the effect that we have this timescale stuff, so that a flow that starts gets more a larger share than long-standing flow. And yeah, so this work is basically how could I say, pursues similar goals as all the Connect stuff. And that means all the use cases that we discussed in the Connect context also apply to this approach.
Hi, Jake Holland. I just want to make sure I understand what's going on here, because this is a pretty different approach to congestion than most of the ones we see. So if I understand correctly, this is going to be within a domain, you can deploy a thing. It doesn't really need tuning. It's got, you can pick values that are defined here, and then regardless, so it's sort of for static non-responsive load, kind of like what Facebook in the IETF Open was describing, the edge thing. Did you see that one? Okay, so forget that. But it's sort of independent of the downstream queuing disciplines. So even if you're talking drop tail, as long as you've sort of got this static demand that keeps happening, then it's gonna force it to back off because it just doesn't get the capacity, right? Am I understanding all this right?
Not quite. So I mean, it's an open loop solution, but you do need to change things at the core. You need to take into account these drop precedences, and that you have to change. And our normal queuing disciplines today are for a single drop precedence.
Right. Okay. Yeah.
So by having, for example, in this work, 4 drop precedences, in some of our articles we have actually 65,000. So by having a number of drop precedences, you can control resource sharing in a open loop way.
Okay.
So you have to support, and we went down to 4 because we believe that this kind of 4 drop precedence behavior can be approximated with the right configuration of current hardware if you configure RAD according to these drop precedences.
All right. Well, that's very interesting. Thank you.
Yeah, Bob Briscoe. Yeah, I wanted to just come back on what Michael said about ABC and Connex and so on. And yes, you're right, Michael. They have the same aims, but I think it doesn't need Connex to do what you're doing, because you're doing this at a one node. Yeah, it's not for a network. Yeah.
It is supposed to be for a network. So if you mark your packets according to that marking at the edge, then all your core routers can take this into account.
But it's just using local information. It's not using any information from anywhere else in the network. Yeah.
At the core, yes, it is only using this packet marking. So but I think also my comment it realizes the use cases of Connex, but it's definitely a very different architecture and solution.
Yeah, and so I think what you'd done, Michael, with ABC was do it at a single node, and then you don't need Connex and everything. You're just using the local congestion information at your local node to do the multiple timescale thing by,
So what you need for drop decisions is both the local congestion information plus the packet value. So it's called here the packet value, and the local congestion information. That's the input for the decision making, whether to drop a packet.
Yeah. And actually, I think as well as ABC, there is a commercial implementation of something like ABC that Eloquia do for their traffic management as well. So you might want to look. I don't think they've published anything about it, but they did say I could say it existed. Yeah. Right.
Thank you so much.
Thank you.
And I'll give you your minute back. Folks, thank you for showing up here, and we'll see you again next time in Montreal. In the meanwhile, keep the list busy, as you have.
I got my